room temperature is, it's 22.9. No, 23.0. So, or something like that. So, room temp is about 23.1 degrees. At least that's what it is up here in the front of the room. And so we're going to start counting cranks when we're 3 degrees lower than that, and then we're going to crank it until we get the temperature 3 degrees above. So let me show you how that's going to work. We're going to pretend I've got water in here. It's kind of tricky to not spill the water out, before you get the apparatus all set up. So the drum has 3 little screws on the bottom of it, and they fit into this black plastic flange. It has, would you mind just showing here? It's got, it has like a large circular opening and then a thinner groove for the screws to fit in. So you're going to line them up and then lock it into place. Okay, there it's locked into place. Now, also in your little Rubbermaid container, you're going to find a peg and a spring. And the peg's got a little hole in it. You're going to thread the spring through that hole. And then you're going to you're going to end up attaching the rubber braid to that. Maybe I'll do it right now. You're going to attach the rubber braid to the spring. And did I say rubber braid? Copper braid. And I'm going to put the peg back there just for now. You may have to adjust, in fact, you undoubtedly will have to adjust the position of the peg. Now here's the part where you always end up, or where I always end up getting a splinter. Oopsie. Okay, so you're going to wrap it around, I can't remember what the lab instructions say, 3 times maybe, 3 or 4 times. And I guess I need to move this a little bit farther here. So what you want to do is turn the crank. Now I don't know if you can tell, I think I'm lifting it a little bit off the, you need to lift it off the floor a little bit. Okay, so let's see. This is like the trickiest adjustment. Let me lift this up. Okay, but I usually like to keep it, you can tell it's freely moving, right? It's not being supported by that blue box anymore. You don't need a blue box, it's just that my table's higher. So now I'm going to do work against friction. There's friction between the braid and the copper drum. And each crank I'm turning it through, I'm moving, it's effectively moving it through one circumference of the drum, right? You with me on that? So the work that I'm doing by turning this is equal to the weight that's hanging from there, 5 kilograms times 9.8 newtons per kilogram, times the circumference of the drum. And so that's the work I'm doing. And then that work is going to be converted into heat, and it's going to warm up the water and the drum and the copper braid. Okay? So, what you're you're going to do is count the number of cranks. Do we have a capital N for that?
Yeah.
I don't see where it tells us to write that down.
Under the suspended from drum.
It's down at the bottom. I see work done on drum, but was it anywhere else? Oh, number 10, number of turns. Duh. Okay. And number of turns, it's going to be like, 300, 250. It's going to be a lot of turns. So the work done by, let's just call it the work done, is going to be the mass that's hanging, which is 5 kilograms, times 9.8 newtons per kilogram, times the number of turns, N, times the circumference of the drum, which is going to be pi times the diameter, pi d, right? That's the circumference of a circle. You're with me on that, right? Okay, so you're going to calculate that. That's going to be some number of joules. And then this thing about the temperature. You want the delta T to be as close to 6 degrees Celsius as you can get it. Now, you might overshoot, or you might end up starting a little late. Well, okay, write down your actual delta T. Don't just say 6, even if it wasn't really. Do you know what I'm saying? All right, now, here's how we're going to try to factor out heat losses due to temperature differences. When the water and the drum are at a lower temperature than room temperature, they're going to absorb heat from the room and warm up in that way. That makes sense, yes? And if it's above room temperature, it's going to radiate heat out to the room, which would tend to lower its temperature. So to balance out those two effects, what you're going to do is make an ice, put some ice in water in, I think, I don't think he put beakers out, which just figures. I'll get some beakers out. You're going to do an ice water mix so that I think that you should be 7 degrees below room temperature. That should be the temperature of the water and the copper drum and stuff when you start to set this up, because when you're touching it, it's going to absorb heat from you, in addition to absorbing it from the surroundings, and then you're going to be messing with it, getting the copper braid wrapped around it, and so on. So you want your initial temperature of your water to be at least 7 degrees. I'm going to say maybe 10 degrees or so below room temperature, which we'll just take to be 23, okay? So you want an ice water mixture, you want a water, you're going to cool it with ice. You want the water to be about 13 degrees Celsius when you put it in here. Then you start hooking everything up. Then when you're all ready to crank, you can start cranking. You're going to crank without counting the cranks until you get it to 3 degrees below room temperature, which would be what? 20. So if you haven't warmed it up to 20 by handling it and getting it all set up, then you'll just crank until you get it to 20. So you're going to start with an initial temperature of 20. And then at that point, somebody needs to be counting the cranks. And you're going to crank until you get it to 26 degrees Celsius. Okay? Now, the heat added to the drum and water, that's like the next calculation they're looking for. And there's a formula for it, right down there. And let's see, maybe I can, you don't have to follow me, whatever, just do it right here. The heat added to the drum and the water is going to be, it's the mass times the specific heat times the change in temperature. Have you seen that before in a chemistry class or a physical science class? The C is the specific heat of the material. Now, for water, the specific heat is 1 calorie per gram Celsius degree, or in terms of kilocalories. Do you know about a kilocalorie is the capital C calorie, and then a lower C calorie is just a plain old calorie? Do you know that? So the specific heat of water is 1 kilocalorie per kilogram Celsius degree. That's the specific heat of water. And the specific heat of copper is given here. Yeah, 0.092. That capital C calorie is a kilocalorie. That calorie is a kilocalorie. It's kind of sloppy nomenclature, but that's what they use. So anyway, you've got the water. So it's going to be the heat absorbed by the water plus the heat absorbed by the copper. And to get the heat absorbed by the water, you've got the mass of the water plus that mass equivalent. That's to account for the thermometer, times the specific heat of the water, times the change in temperature of the water. And the change in temperature is going to be, hopefully, it's going to be 6 degrees, 26 minus 20. That should be our delta T. So that's the water part of it. And then the copper part, well, let's see, we've got the copper drum and fair Joule and the copper band. So you need to measure the mass of the copper band also. So the mass of all the copper times the specific heat of the copper times the same delta T. It's still 6 degrees. I know. Hang on. So that's going to give you something in kilocalories. And what they're asking us to find is the ratio of the work to the heat, to the kilocalories. And they tell us down at the bottom, compare the ratio to 4,186 joules per kilocalorie. So in the end, you're going to calculate work divided by heat, and you're going to compare that to the accepted value of 4,186 joules equals 1 kilocalorie. This is the accepted value. So that's what you want the percent difference with. Okay, so you got it? You understand what's going on? Okay, go do physics.